here. And Steve, Tani, I'll hand things over to you.
Thank you very much, Troy. Before I get started, I'd like to say that I am honored that Jim Matheson is here with us as part of the group this evening. Jim was the director of the Decision Analysis Group at Stanford Research Institute when I joined that group, and I'm going to say it's 46 years ago.
Wow.
I guess that dates us, Jim.
Yeah,
and so he was my boss, my colleague for a number of years when I worked at SRI. And so I'm honored that Jim is here. And I think he can keep me honest this evening if I make any mistakes. Okay, I'm going to share my screen. And hopefully you can see the title of tonight's talk, 5 Rules of Actional Thought. Okay.
Yes.
All right. So we present here a normative view of decision making that describes how we aspire to make decisions. Now, this contrasts with a lot of work that's going on in descriptive decision making, that is, study of how people actually behave when making decisions. So there's a really large body of research that show that people often make errors when making decisions in these kinds of situations. We find this research useful in our profession because it points out common errors that we then try to avoid when we're helping people make decisions. But for a description of how we want to make decisions, we turn to this normative theory. Okay, so we're talking about the normative theory. Decision theory is kind of analogous to Euclidean geometry in that it's founded on a small set of rules, or in geometry, they're called axioms. So as I'll point out this evening, the theory of good decision-making really resides on just 5 rules of rational behavior. And whereas the axioms of geometry are statements about the external world, the shortest distance between 2 points is a straight line, the rules of decision-making are statements about how the decision maker wants to behave or chooses to behave, okay? These rules satisfy the requirement we would want of any set of fundamental rules, such as the rules of arithmetic. They're correct when they're applied to simple situations, and they extend to more complicated situations without breaking down. So they're very strong fundamental set of rules. The theory that rests on these rules states that we must make decision choices in a particular way if we want our actions to be consistent with the rules. So we call these rules the rules of actional thought, the thoughts we have about taking action. I think that's a Ron Howard term, or the actional thought. There have been several somewhat different formulations of rules for decision making. So back in the 1940s, in a very seminal work, John von Neumann and Oscar Morgenstern stated 4 axioms of rational decision making. Their work is called Theory of Games and Economic Behavior. And they showed that these axioms imply the existence of what we call a utility function, and that decisions must be made to maximize the expected or mean utility to be consistent with the axioms. Now, about 10 years later, Leonard Savage proposed a somewhat different axiomatic theory that explicitly includes the use of subjective probabilities. The 5 rules I'm going to present tonight were actually created by Professor Ron Howard at Stanford, my PhD advisor, and colleague of Jim Matheson's. And so this formulation is based on what he calls the 5 rules of actional thought. Okay, so let's go through the rules. Rule number 1 is the probability rule. This rule says, I can describe any decision alternative as a set of possibilities to each of which I can assign a distinct probability. Okay, so we often talk about a decision alternative as a deal, the term deal, that can be expressed as a probability tree. You think of that. When we're talking about probabilities on events, because I cannot change the past, the only consequences of interest to me in any decision are those that occur in the future. And so one of the consequences of the theory of decision making that's based on these rules is that we choose to avoid thinking about sunk costs as being relevant to the decision. Saying that I don't have a probability for that event is a violation of this rule. So it's okay to say, boy, I really have to think hard to get a probability for that event, but the probability is there even though you might have to work hard to get it. Okay. So think of this simple example. Let's suppose we're thinking about going camping as an alternative for a vacation. And there are two uncertainties. There's what kind of weather we're going to experience when we're camping. And the second uncertainty is how crowded the campground will be where we're going to be. One of the features of talking about possibilities is that the distinctions of weather and level of campground crowdedness that we're talking about must be defined in such a way that they pass the clarity test. Now, the clarity test, one way of thinking of that is that the distinction is clear enough that if we asked the clairvoyant what was going to happen, the clairvoyant wouldn't say, oh, well, you need to define clear more, with more clarity. What do you mean clear versus rainy? Okay, so the distinction definitions need to be stated with enough clarity that if the clairvoyant were there and we asked the clairvoyant what was going to happen, clairvoyant could answer without further questions. Okay, and the probabilities that we assess for the possibilities express our beliefs regarding the likelihood, the relative likelihood of their occurrence. Okay, so-called subjective probability interpretation of these probabilities. Okay. Now, in just a minute, we're going to talk about how we feel about the so-called outcomes or prospects. If we go to camping and the weather is clear and the campground is not very crowded, it's uncrowded, boy, that's great. Okay, so we're very happy. On the other hand, the bottom, if we go camping and it's rainy and the campground is crowded, that's terrible. Okay, so that's really has to do with the next rule I'm going to talk about, the order rule. So the order rule says, if I'm given a set of prospects, I can put them in a list from best to worst according to my preferences. The one that I prefer the best down to the one that I prefer the least. Okay. Now the word prospect is defined as my future life, assuming that I've selected an alternative in the decision and that a specific combination of the relevant possibilities have occurred. So if you think of a decision tree, a prospect is at the end of the tree. It says, oh, you've chosen this alternative where there's a decision node, and these sets of uncertainties have resolved in a certain way to get to this point at the end of the tree. Okay, and so given those outcomes at the end of the tree, the order rule says I can put them in order of my preference. Now it's okay if two or more prospects are tied in order of preference. I'm indifferent between those two, that's okay. Sometimes there may be a prospect that's difficult to rank because of ambiguity or I would say uncertainty in it. And if so, we need to add distinctions to make the prospect easier to put in rank ordering. So the example is, if I'm thinking about getting a new dog or getting a new stereo system, and I'm unsure how to rank those, it may be because if I get a dog, I'm just not sure if it's going to take a lot of time to care for or not not much time. And so in that case, I need to add, as part of the distinction, getting a dog that's easy to take care of or getting a dog that takes a lot of time to take care of. And then perhaps I can rank order those prospects. Okay, here are 4 prospects. If you were offered these 4, think about how you would rank order them. A is being invited to join the current president and first lady for a private dinner at the White House, all expenses paid. B is to see your favorite sports team win a major championship. C is to receive a non-transferable 50% discount on anything you buy at Starbucks, valid for 1 year. And D is to receive a non-transferable lifetime subscription to the National Geographic magazine. Okay, so the order rule says, even though these are very different kinds of things, you must be able to put them in rank order according to your preferences. Okay. One of the reasons why the order rule is important is that it keeps us from becoming what's called a money pump. One of the consequences of the order rule is that preferences are what's the word I'm looking for? Transferable? No, that's not the right word. So if A is preferred to B and B is preferred to C, then A must be preferred to C. You can't have A preferred to B, B preferred to C, and C preferred to A. Okay, that's a violation of the order rule. If you violate the order rule, then you can be turned into what's called the money pump. Here's an example that comes from Ron Howard, I think. Suppose I own a Volkswagen, but I really prefer a Volvo because it's safer than a Volkswagen. So I'd be willing to pay money to someone to take my VW in exchange for a Volvo. So now I've got a Volvo, but now I look at a Jaguar, and now I prefer the Jaguar to the Volvo because it's just much more stylish. So I'd willingly pay money to someone to take the Volvo in exchange for the Jaguar. So now I have the Jaguar. But now I'm thinking about how much more reliable the Volkswagen is to the Jaguar. And so I prefer the Volkswagen to the Jaguar. So I pay someone some money to take the Jaguar in exchange for the Volkswagen. So what have I done? I've paid money 3 times and I wind up where I started with the same car, the Volkswagen. Okay, and I could be taken around that cycle again and again. That's a money pump. So violating the order rule is something you want to avoid. Okay, rule 3 is called the equivalence rule. This says that if you have 3 prospects, A, B, and C, such that you prefer A to B and B to C, so the ranking is A, B, and C, then you can specify a probability P such that you're indifferent between receiving B for sure, the middle one for sure, or a deal with probability P of receiving A and probability 1 minus P of receiving C. Okay. So the rule says that there is a probability P that would make those 2 deals, B for sure, or A or C with probabilities, equivalent in preference to you. This probability P that we're talking about is called a preference probability because it's an expression of someone's preferences, not that person's beliefs about the likelihood of future events. Okay, and in fact, the preference probability might be quite different than the probability that expresses the person's belief about the likelihood that the event will occur. Okay, so it's a preference probability, but the equivalence rule says that you must be able to specify a probability P such that that equivalence holds. So here's a simple example. Let's suppose that A is you receive a cash prize of $500. B is the status quo where you are now, and C is no cash prize, but you get a really bad cold for a week. You have bad cold symptoms for a week. Okay, and so for most people, A is preferred to B and B is preferred to C. And the question is, what is the probability P for getting A such that the probability the deal where you get A with probability P and C with probability 1 minus P has the same, you have the same preference for that as B for sure. Okay. Well, clearly, if P were 100%, okay, if the cash prize were for sure, you would prefer the uncertain deal rather than B. Okay. Whereas if P were 0, so that you get the bad cold symptoms for sure, you would prefer the status quo to the uncertain deal. And so there's a P in between 100% and 0, such that you're just indifferent between B for sure and this uncertain deal between A and C. Okay, that's that preference probability. Okay. All right. The fourth rule is called the substitution rule. And this rule says, if I face a situation as described in the equivalence rule, in which my probability of receiving prospect A happens to be equal to the preference probability I've assessed, then I will be indifferent between receiving the uncertain deal or the middle prospect B for sure. A lot of people, and I think I was one of them when I was a student, when I first saw this, I scratched my head and I says, well, didn't we just say that? You know, isn't that what the equivalence rule says? But this rule is actually necessary. We sometimes call it the do you really mean it rule. And what it means is that we can use preference probabilities in the analysis, treated as real probabilities in the analysis when we're looking at decision situations. Okay, but you can think of it as, do you really mean it when you make that equivalent statement? Okay, and the fifth rule is called the choice rule. Now, this one's pretty easy, I think. This says, imagine that you're given a choice between two deals offering different probabilities of receiving the same two prospects. Okay, so each of the deals has two possible outcomes, and the outcomes are the same in each deal. Okay, so in this example, we'll go back to the $500 cash prize versus the bad cold symptoms. Deal one is you get an 80% chance of the cash prize and 20% chance of the bad cold symptoms. Deal two, which you could choose if you want, is a 60% chance of the cash prize and a 40% chance of the bad cold symptoms. The choice rule says that if you prefer the first prospect to the second, you must choose the deal that has the higher probability of the more preferred prospect. You must choose, in this case, deal one, because a higher probability of the prospect that you prefer. Okay. And, you know, if someone said, no, I don't want to behave according to that rule, I think people would scratch their heads. They say, what? You know, it's just so self-evident that that's what you'd want to do, that a violation would be considered nonsensical. Okay, so those are the 5 rules. And guess what? Turns out that all of decision analysis rests on the foundations of these 5 rules. I'm going to show you an example that a decision can be made by the direct application of those rules. But in fact, the way decision analysis is normally done is we apply the rules in a more simplified manner by mapping all the prospects to a quantitative value measure that describes a fungible and alienable resource. The measure is often, maybe usually expressed in monetary terms. So if we do that, the rules imply the existence of what Ron has called the U curve. It's a non-decreasing function that specifies a U value for any amount of the value measure. And then if we have that U curve, I can find a U value for each prospect, calculate the probability weighted average U value, expected U value for each alternative. And the 5 rules require that I choose the alternative with the highest mean U value, highest expected utility. And then we can go back to the U curve to determine what the monetary amount is that corresponds to that mean U value. We call that the certain equivalent. Okay. And in a lot of decisions, the applicable portion of the U curve is very much a straight line, or essentially a straight line, so that we can make decisions based on the mean monetary value, the expected monetary value, rather than actually taking a translation into the U-curve and back. Okay. There are some restrictions on decision making that come with compliance with the 5 rules. One of them is that if you have a set of alternatives and you've done the analysis and you have a rank ordering of them in preference, if you were to remove one of the alternatives from the set of possible alternatives, you say, I'm choosing between vanilla, strawberry, and chocolate ice cream. When I think I like vanilla better than strawberry, better than chocolate. If the clerk behind the counter says, "Oh, I'm sorry, we don't have any strawberry today," that information cannot change the rank ordering of the remaining alternatives. You can't say, "Oh, in that case, I prefer chocolate to vanilla." Okay, that's a violation of the rules. Okay, same thing if you add a new alternative, it cannot decrease the value of any of the other original alternatives. Okay, and as I said before, sunk costs cannot be considered as part of an important part of a decision, that they need to be ignored. And then a very strong statement here. Putting value, usually negative value, on regret, possible future regret for what might have been, is a violation of the rules. Okay, doing that it violates the rules. So here's a little example. Let's suppose that you're a plaintiff in a civil lawsuit that's just about to be decided in court, and you're walking up the steps of the courtroom, and the lawyer for the other side intercepts you on the steps and says, we'd like to offer you some money to settle out of court. Okay, so now you have a decision. Okay, do I settle out of court, and let's say the offer was $400,000, or do I say no? Let's go in and have it settled in court. And if I win the lawsuit, I know I'm going to win $2 million. But if I lose the lawsuit, I get nothing. Okay. Well, if in your tree you say, oh, if I don't settle and I lose the lawsuit, not only will I get $0, but boy, I'll feel like I'll be kicking myself that I didn't settle out of court. Okay. Well, the statement here is putting that regret as part of the outcome to be evaluated in the tree is a violation of the 5 rules. That's not a part of the set of prospects that you should be thinking of. Okay. All right. Let me show you how the 5 rules can be applied to resolve a decision situation. This is one that I made up very recently. It's called the Champ Souvenirs Decision Problem. And the situation is the following. There's a small company called Champ Souvenirs, and they've just won a 1-year contract to supply souvenirs for sale at the home field of a minor league baseball team called the Mudville Beavers. Okay. And in this business situation, at the start of, or just before the start of the season, Champ has to place a single order with its supplier for souvenirs to be sold that whole year. In other words, it's, before the season starts, you have to decide how many souvenirs you're going to have in inventory. Okay. And to make things simple, let's say there are only 2 alternatives: a big order or a small order, big inventory or small inventory. Now, the problem is that demand for the souvenirs that year will either be strong or weak, depending on how well the team does. If the team goes on, wins a championship, there'll be lots of fans there toward the end of the season, and they'll be very excited and enthusiastic, and they'll be buying souvenirs right and left. But if the team doesn't do well and they down in the middle or bottom of the league, then the number of fans will drop off, and they won't be very interested in buying souvenirs. Okay. So again, we're going to make it very simple that demand is either strong or weak. And Champ Souvenirs, looking at the information it has, says, I think those are equally likely outcomes. Okay. And of course, Champ wants to act consistently with the 5 rules in making his decision. So we start by drawing a decision tree. There are 2 alternatives, big inventory and small inventory to order. And then there's the uncertainty about the level of demand, strong or weak. And we put the assessed probability, the probability that the company has assessed, a 50% strong, 50% weak, on the tree. And that's consistent with the first rule, the probability rule, okay, that Champ can assess a probability for each prospect in this case. There's only, in this case, only that one. Okay, now there are 4 outcomes in this tree. Big order size, strong demand, big order size, weak demand, and small strong and small weak. According to the order rule, the decision maker, Champ, can rank these 4 prospects from best to worst. So the best one would be buying a big inventory and having strong demand. Wow, that's great. We'll make a lot of money. You hit the jackpot. And the worst one, according to Champ, is we order a big inventory and demand turns out to be weak because we will have spent a lot of money and we don't bring very much money in. And the souvenirs, this is a 1-year contract. And so, we have to throw the unsold souvenirs away. So we have big losses. And then the 2 prospects in the middle, turns out that small inventory and weak demand is the second highest ranking prospect, okay? Because we make modest profits. And somewhat worse than that is small inventory and strong demand, because not only do we make modest profits, but we have to deal all year with the hassle of unhappy potential customers. Customers come and say, we want to buy a pennant or a hat or something. We say, oh, I'm sorry, we've run out, and they turn away and they're very unhappy. So that's a less desirable outcome. Okay, so this is the rank ordering of the prospects, and the order rule says that that ordering can be made. Okay, now we're going to employ the equivalence rule by imagining a deal on the best and worst prospects. Okay, remember the best is big strong and the worst is big weak. Okay, we're going to imagine a deal on those 2 prospects and find the preference probability that makes that deal equal in preference to each of the middle prospects. Okay, so of course, big strong, the one at the top, the preference probability is 100% best because that is big strong. Okay, and the one at the bottom, 100% worst, is because worst is big weak. Okay, so the top and bottom are easy. But let's think about small inventory and weak demand. The Champ thinks about that and says, well, gosh, if I were given a 62% chance of big and strong versus a 38% chance of big and weak, that would make me about indifferent between that deal and having for sure a small inventory and weak demand. Okay, so that's it takes some thinking. What is it? You might start with a number that's high, like 90%. Oh, I think I'd take the uncertain deal for sure. Go down to maybe 10, 20%. Oh no, I would take small weak for sure. And then you find the probability that kind of makes them equal in preference on your preference scale. And that's called a preference probability, as I said before. Okay, so let's imagine that Champ says, okay, my preference probability for small weak is 62% chance of the best versus 38 for the worst. And for small strong, it's less than that because it's a less desirable prospect. So it's a 44% chance of best and 56 chance of worst. Okay, so now we have a deal on best and worst that is equivalent to each of the outcomes in the original tree. Okay, so what we do is we actually put that in at the end. So at the end of each tree, okay, we say, well, let's put in that equivalent deal. All right, and so that's we're employing the substitution rule in doing that. Okay, so here's our tree. If we order a big inventory, there's a 50-50 chance that the demand is strong versus weak. If it's big and strong, then the equivalent deal is a 100% chance of best and 0% chance of worst. If it's big and weak, the equivalent deal is a 0% chance of best and 100% chance of worst. Okay. Down here, if it's small and strong, then the equivalent deal is a 44% chance of best, 56% chance of worst. And small and weak, there's that 62% chance versus 38% chance. Okay. Now we can multiply through the probabilities to find the probability of best and also the probability of worst for each alternative. Okay. If the order size is big, there's a 50% chance that demand is strong and 100% chance that we'll get best. Okay. So there's a 50% chance that we'll wind up here with best. Down here, 50% chance of weak, but a 0% chance of best. And so here it's 0. And so the sum of these two probabilities is the probability that we would get the best outcome, the most preferred outcome, if we chose the big order size alternative. If we chose small, 50% chance that demand is strong, there's a 44% chance we get the best in that case. If the demand is weak, there's a 62% chance of best. Well, 50% times 44 is 22%. 50% times 62 is 31%. And so the sum of those two, 53%, is the probability that we would have of getting the best prospect if we chose the small order size. Okay, so I'm going to simplify the tree, show it this way. Here's our decision alternative, big and small, and the equivalent deal. Okay, if we chose big, there's a 50% chance of the best and a 50% chance of the worst. If we choose small, there's a 53% chance of the best and a 47% chance of the worst. Okay, and according to the choice rule, we must choose the alternative that has the higher probability of the more preferred prospect, in this case, the best. And so this says, according to the choice rule, we must choose the small inventory size. Okay, so that's essentially the way we use the 5 rules directly to resolve a decision situation. Now let me step back a little bit and say, imagine, before I go on, let me make this important point. Notice that if the choice is small, okay, we're not saying that there's a 53% chance that Champ is going to get the best outcome. There's no chance he's going to get the best outcome, right? Because the best outcome is big and strong, and he's already choosing small. Okay, so this 53% is still a preference probability. Okay, so we're not saying, you now have a 53% chance of best. No, this is a preference probability that we're calculating in order to see which alternative to choose. Okay, let's suppose that we define a value metric in which the best prospect is worth 100 points and the worst is worth minus 60. Okay. In that case, finding the preference probabilities such that the uncertain equivalent deal has the same preference as each of the internal prospects, is equivalent to finding the value on that value metric for that prospect. Okay, so in fact, we can do the arithmetic. We can say 62% of 100 plus 38% of minus 60. It turns out to be 39. Okay, or you can think of it as the decision maker saying, well, if big and strong is plus 100 and big and weak is minus 60, then small and weak is, it's about, it's about 40, it's like 39. Okay, so that assessment could be done kind of directly, and it's really the same assessment. Okay. Okay, it turns out that the metric for small and strong turns out to be 10. Okay, so if I put these four metrics, the value metrics, on the original tree, we get a tree that looks, very familiar. Okay, if we order big, there's a 50% chance we'll get something that's worth 100. If we order a 50% chance we'll get something that's worth minus 60. Okay. If we order small, a 50% chance we'll get something that's worth 10, a 50% chance something that's worth 39. We can calculate the expected values of the metric. In this case, it's 20 for big and about 25 for small. Okay, and we can see by that comparison that we should choose the small alternative. Okay, so this is more like how we normally do decision analysis. Okay, we're using value metrics normally, but it's basically the same process that I showed you applying the 5 rules directly. Okay. One advantage of doing it this way is we can say, oh, look at this. The small alternative is 5 value units more preferred than the big one. And if these were hundreds of thousands of dollars, thousands of dollars, then we could say, the small one is worth $5,000 more than the big one. Okay, that's it. Are there any questions or comments?